Here's another application problem where they're asking us to either maximize or minimize something. This example says a piece of sheet metal is 9 centimeters by 9 centimeters. Square corners are cut out so that the sides can be folded up to make a box. Let X represent the length of the cutout squares. And so you see over here in the picture that they have provided that they have let the length X be the length here that we're cutting out. So if we were going to see the squares, that's what they would look like, but then you cut them out, and so the length and width of those squares are X. First question is, give a function that represents the volume of the box. Okay, first of all, recall that volume for some kind of box-shaped thing is the length and width of the base, so it's length times width times the height of your box. Okay, in this situation, what I will do is to represent a function, I'll use v of x equals, and then we need to know the length and the width of the base of my box. On here, we know that the total distance from here all the way to here is given as 9 centimeters. Well, we have an x that was taken out of each side. In other words, x was taken away here and x was taken away there, and so the remaining distance from here to here would be 9 minus 2 x's. And so this particular length would be 9 minus 2x. Because this is a square piece of sheet metal, in other words, it originally measured 9 by 9, we can say the same thing for the distance from here to here. That would also be 9 minus 2x. And so the base of our box would be 9 minus 2x times 9 minus 2x, which is the same as 9 minus 2x squared. So that would be the length times the width of the base of that box. Now, if we're cutting out square corners, and those square corners are represented by x, when we fold the corners up, then the height of the box is going to be x. And so there's the function that represents the volume. Now, on this particular piece, where they ask what the domain of the function is, this is a little bit trickier than problems we've worked on in the past. Now, first of all, we know that domain has to do with x. And we see in this problem that x is representing this cutout part that represents, me being able to create my box. I know that x must be greater than 0, so I know that for sure. But I also have another element that plays a part in the domain, and that is the length and width of the base of this box. I know that any kind of length or width must also be greater than 0. So in this case, to find the domain, I want to take the expression 9 minus 2x, and I'm going to set that strictly greater than 0 and solve. Doing that, I would need to subtract the 9 over, so negative 2x would be greater than negative 9, and then I would need to divide out the negative 2. When I divide by a negative, that sign needs to switch, so it becomes x is less than 9 halves, and then 9 halves is equal to 4.5, and so my x's would need to be strictly less than 4.5. So on here, my domain would be set of all x so that not only must my x's be greater than 0, but my x's must also be less than 4.5. And so my domain would be written like this. So for this particular problem, the domain, we have a maximum that our domain can possibly equal because of the length and the width of the base of the box. Last question, find the value of x that would yield the maximum volume. So because it's asking for a maximum volume, we would need to enter in our calculator our volume function. So y1 would equal 9 minus 2x raised to the second times x. And let's go ahead and enter that in our calculator. So go to y equals, clear out anything that you might already have in there. And then we have parentheses, 9 minus 2x, close parentheses, raised to the second. I have to right arrow, and then multiply by x. For this one, we figured out the domain, but to set a window, I would need to also think about range. So let's do this. On the window, we've said because of our domain, the lowest the x could be would be 0, the most the x could be would be 4.5. Now think about what the y value was. The y value is a volume. Volumes must be bigger than 0, so we would let 0 be the minimum of this particular function. As with other examples, we're going to have to play with the high value. Okay, I know it's going to be relatively large. Let's say 100 here, and then I can play with that high y value. If I need to make it larger or smaller, I can. So let's go to Window, do 0 to 4.5, don't do anything with the scale, and then 0 to 100. That 100 is no magic number, it's just a number you're going to have to play with, and then go to Graph. Okay, in this situation my 100 was actually high enough, so we see the whole graph is represented in that window, so my window's good. I'll sketch the graph. And then on here, make sure you label your axes. In other words, the horizontal axis was x values, and then on this one, the vertical axis was v of x, which was volumes. I want to specifically find the maximum, and so on the calculator, I would go to second trace, option number 4, which is maximum, and then ask for a left bound. So I need to arrow up. We see that flat place at the top. I need to go to the left of it and off of it. Press enter, and then go to the right of that flat place, fall off that side, press enter, and then when it asks for a guess, press enter again. And in this case, it looks like my ordered pair is 1.5 if I round that, and then 54. Alright, let's go see what this question specifically asked. It said find the value of x that's going to yield the maximum volume. So we know that because this axis is our x value is 1.5. Okay, so we would say, so x equals 1.5. We need to look back up at the top for units. The x is a length or a width, so it's centimeters. So 1.5 centimeter yields the maximum volume. Now the problem didn't ask for it, but if it asked for the maximum volume, we know the maximum volume would be 54 cubic centimeters.